Okay, so the topic of today's lecture is expected values for joint random variables. And also, now that we're dealing with two random variables, we can start to talk in more interesting ways about how those random variables are related to each other, okay? So today's topic is basically expected values or expectations for joint random variables. And also, we're going to talk about these concepts called correlation and covariance, and again, come back to this kind of idea of independence. Okay. So, recall from one random variable that we basically introduced this idea of expected value, right? The expected value of some function of x was what I would get if I integrated that function. You know, I could say, for example, g of t times the PDF dt, right? So the easiest example of this is just like the expected value of x itself. The mean I would define as integrating t times the PDF dt. Okay. So for two random variables, you know what you're going to get, right? So if I have a function of two random variables, g of both x and y, what I would do is I would integrate that function. And here I'm going to use something like, you know, uv du dv, right? So I take the function, I multiply it by the PDF, and I do a double integral, right? And what comes out is some single scalar number, right? And so the nice thing is that just like for one random variable, we can use all these nice like linear properties of expectation, right? So expectation or expected values are linear, which means that the expected value of ax plus by is equal to a times the expected value of x plus b times the expected value of y. So I can always kind of take expected values apart to be a little bit easier, right? And just kind of as an exercise, you know, let me just convince you why that's true, right? So if I just plug in my definition, right? This would be like saying, okay, I'm going to integrate this function, which is going to be like au plus bv times this PDF and I can see that I could take that apart into just the part that depends on au du dv plus the part that depends on v, bv, like this, du dv. And then, you know, so this is just a constant. These constants can kind of come out to the outside of the integral. And then what I'm left with is something like, you know, a times this double integral. I'd have something like u f of xy uv du dv, plus I'm not going to do this second part, just let's follow along with what happens here. So this is like saying, okay, well, if I'm integrating like this outer part, right, forget about the u, if I move the u out, this is kind of saying if I integrate the PDF dv, what I get is just the marginal, right? I just get what we called the marginal in x of the PDF of u, right, or of x. This is like saying, you know, I don't care what v is, integrate that out from minus infinity to infinity. What I end up with is just the marginal PDF of x, and then this u times this PDF is what we defined as the expected value of x, right? So you can kind of see that everything works out as it should. And then just in the same way, there are, oh, so let me pause and ask questions or comments about this basic idea. I mean, really everything that we do today is just stemming from this definition, which is something that really you should already kind of get a sense of from how we defined PDS before. So just like in 1D, we had this notion of what we called moments. We didn't hit this concept like super hard, but basically for one random variable, we defined the kth moment, which was the expected value of x to the k power, and we also defined what was called the kth central moment, which was the expected value of x minus the mean to the kth power. So for example, the second central moment is what we gave a name to as the variance, right? That's like the expected value of x minus the mean squared. So those kind of concepts transfer over to two random variables, except now we could raise one of the variables to one power and the other variable to the other power. So there are these definitions of things like, for two random variables, we could have, for example, kind of like the j comma kth moment, which would be the expected value of x to the j, y to the k. And then the j kth central moment would be the thing that I would get if I subtracted off the means first, right? So I could say expected value of x minus the mean of x to the j power, and then y minus the mean of y to the k power. And so as you can imagine, this could get really tedious if I actually asked you to compute like, oh, compute the third central moment of blah, blah, blah. It would be a lot of work, right? So I'm just kind of giving you these definitions so you kind of see the bigger picture, okay? All of these things give me a sense of how x and y are kind of related to each other, right? And so in particular, what I want to talk about particularly is just the expected value of x times y. We give that a special name. So let me just say that these give us a sense of how x and y are related. Okay. But I'm going to give one of these a special name, similar to how I named the variance. If I let j equals k equals 1 and talk about the expected value of x times y, this has a special name, and this is called the correlation of x and y. And if I subtract the means off, this is called the covariance of x and y. So it's important to know what, if I tell you to compute the covariance of something, these two words are really important to make sure you know and to not get them mixed up, right? Correlation is just straight out expected value of x, y. Covariance is doing the same thing but subtracting off the means. Yes? So particularly when j equals k equals 1, right? So basically if I plug in 1 and 1 here, right, we give these two special cases these names, right? Other questions? Okay, so let's just take a look at the covariance for a second. So often we'll call this cov xy, right? And one thing to note here is that if I work this out, just by definition, this is like saying I have xy minus mu x times y minus x mu y plus mu x times mu y. I can break this up into the expected value of xy minus mu x times the expected value of y minus mu y times the expected value of x plus these two means. And I can see that I get expected value of xy. This is mu x times mu y. This is mu x times mu y. So basically I have something like this. So it's basically the correlation minus the two means. And you can see that this kind of resembles the same thing that we did with the variance, right? So the variance we could also expand out to be the expected value of x squared minus mu squared, right? And that's not really a coincidence, right? Because if, for example, I didn't know what I was doing and I said, okay, here's y, but y is the same as x, the very same thing as x. So if I had something like, you know, the covariance of x against itself, if I plug in what I get, that's like saying I'd have the expected value of x squared minus mu x squared, which is actually the same as what we called the variance, right? So basically, you know, the covariance is what we get when I take a random variable times another random variable, and the variance is what I get if I take the random variable against itself. It's like the self covariance, right? So, you know, that's why it has the word variance in its name. Okay. So, questions about this? All right, so one key concept for today is what happens if the two random variables are independent, okay? So important that I'm going to put this on a separate piece of paper. So if x and y are independent, what did we talk about last time? What did I tell you? So we learned that the PDF for independent random variables splits into an x part and a y part, right? Basically, the joint PDF is the product of the two marginals, right? So what would that imply for computing the correlation? So the correlation if I just compute the expected value of x times y, well, that's the definition of I take xy, then I take the joint PDF. Sorry, I kind of messed this up, like this. So this is the definition of correlation, right? xy times the joint. And now I say, well, okay, if I'm independent, then I get xy, and the joint decouples like this, dx dy. And then this also kind of decouples. There's a part that only depends on x and a part that only depends on y. This is the mean in x, and this is the mean in y. Okay? So what did we learn? We learned that the correlation is the same as the product of the means. And then, I'm going to write it again over here. If x and y are independent, I'm going to just restate what I said. This expected value is the same as this product. And the covariance of x and y, which is defined as the correlation minus the product of the means, is 0. Okay? So that's really important. So x and y independent means that the covariance is 0. And in this case, we say that the two random variables are what is called uncorrelated. Okay? So what did we just show? We showed that, you know, x and y being independent implies that x and y are uncorrelated. Okay? So the important thing is that the reverse is not typically true. So I can have the covariance equal to 0, but have dependent random variables. And I'm going to do an example of that towards the end of class, okay? So kind of, one way is easy to show. The other way, I'm going to do an example that shows that I could still have, the covariance being 0, but the variables being dependent, okay? So this is a little bit hand-wavy, but kind of one way maybe to think about it is that the covariance is kind of more like a numerical statement about just the behavior of the two random variables. And I can coincidentally get that behavior to end up with having 0 covariance, but I could still have the two variables be related to each other in a very deep way, right? And so kind of like, correlation is kind of like a numerical coincidence, and independence is like a deep relationship between the random variables. And so it's possible to have the coincidence without also having the deep relationship. So I'll do an example of going the other way in just a second. But let me just pause and ask questions or comments. So let me do a couple of examples of the kind of, crank and, plug and chug procedure that you usually use to solve these kinds of problems, okay? So let's do an experiment, right? So let's suppose that I have a joint PDF that is equal to x plus y for x and y in the range 0 to 1. So you would need to take my word for it. In the first place, this is even a valid PDF, right? Because it's not like totally obvious that this integrates to 1, but suffice it to say that it actually does. Okay, so this is my joint PDF. And now I can say, what is the covariance of x and y? Typical kind of homework problem, okay? Well, for this, I need to compute the expected value of x, y, and I need to compute the means by themselves, okay? So it's kind of a good experiment, right? So I can compute expected value of x is going to be the integral of x times the joint PDF well, this is, I guess that I can already kind of just substitute these from 0 to 1, right? Because I'm doing the real PDF. So now we settle in for a little bit of integration. Doesn't really matter what order I do it in. So I'm going to do the x part first, I guess. 1/3 x cubed plus 1/2 x squared y, evaluated at x equals 1, x equals 0, dy. So I'm going to get 1/3 plus 1/2 y dy, which equals 1/3 y plus 1/4 y squared from here to here. So I'm going to get 1/3 plus 1/4 is 7/12. Okay? So that's the first part of this. And actually, by symmetry, since x and y basically play the same role and they're defined over the same area, I can already kind of visually see that the expected value of y is going to also be 7/12. So I'm just going to say that because I'm a professional. So all that's left for me to do is to compute the expected value of xy, which is going to be from 0 to 1, 0 to 1, xy times the joint, which is equal to just some integration on a rainy day, soothing and mindless. So let's do the x part first. We get 1/3 x cubed y plus 1/2 x squared y squared, x equals 1, x equals 0, dy equals, so we got a 1/3 y plus a 1/2 y squared dy, which is equal to 1/6 y squared plus 1/6 y cubed, y equals 1, y equals 0. So I get 1/6 plus 1/6 is 1/3, okay? So pro tip for, homework and exams, right? So if you want full credit on exams, to show me that you actually know how to integrate, I don't want to see like, expected value of x equals 7/12, right? I mean, like, I want to see that you didn't just plug this into your calculator and get an answer, right? And you can see that I'm whipping this out pretty fast, so it's certainly doable on an exam to do these simple polynomial integrals, right? If you want full credit, you got to show me that you are actually using your brain, okay? So then what would the covariance be? So the covariance would be expected value of xy, which is 1/3, minus the mean times of x times the mean times y. And what do I get? I get, did I actually not compute this here? Well, it's going to be, what is the numerator going to be? Now I got tired. It's going to be 36 over 144. Is that right? That can't be right. 4 times 12, 48 over 144, right? Minus 49 over 144 is minus 1 over 144. That's the covariance. So x and y are correlated, right? Because this answer is not 0. So the opposite of uncorrelated is correlated, right? And one thing to note here is that the covariance, unlike the variance, right? So the variance, when I just look at the variance of x, is the expected value of some squared something. So that's got to be at least 0. But here, the covariance between two generic random variables could be negative, right? As we saw here, it turns out this was a negative number. So just be aware that that can happen, okay? And what I'm going to talk about in just a moment is, what we kind of like to be able to do is to look at this number and interpret it to say, okay, well, really, how related are x and y, right? We want some sort of like a scale for understanding are x and y like really related, or are they just a little bit related? Looking at just the number by itself is kind of tough to judge, right? So I'm going to talk about that in just a moment. But let me just ask, are there any questions about the numerical procedure I did here? Yeah.
So then, is there like some kind of difference between like a negative and a positive covariance, and one being more associated with correlated versus uncorrelated?
Yes, good question. We're going to come to that in just a second. The question is basically, what does a negative number tell you versus a positive number, right? And how does this, so we're going to talk about kind of like how to interpret this number in just a second. Okay. Other questions? Yeah. No. So will the expected value of x always be symmetric to expected value of y? No. Just happens to be true in this case, right? Why did it happen to be true? Because if I look at the, so what would be the procedure I would have had to calculate for expected value of y? It would be this integral, right? dx dy, right? And if I kind of compare this to this, I can just see that if I change the name of x to y, I would get the same integral, right? But if I had something different, where suppose that my PDF was something like, some constant times x squared plus y, where the terms were different, I definitely get something different, right? So yes, don't assume that it's always going to be the same for sure. Other questions? Okay, so let me just take a quick pause to say that another kind of typical question is, now that you know some of these pieces of information, these kind of partial moments, right? So I computed expected value of x, I knew expected value of y, I now have the expected value of x and y. So now if I asked you for something like, okay, compute the expected value of x times 1 plus y, I would expect you to say, oh, well, I don't have to do this as a complicated integral. I can just notice that this is like the expected value of x plus the expected value of y, and I know both of these things. I could just pop this right off based on my pre-computation, right? Just like a one-shot deal. So definitely be on the lookout for, if you're given some sort of expected value thing that looks a little bit complicated, that maybe you've already computed everything that you need and you don't have to do any integration, right? So just be aware of being smart about what you have to evaluate and what you don't have to. And again, just like on the first exam, and for for continuous random variables. Oh, I guess we didn't actually do continuous random variables on the first exam. So on the cheat sheet that you prepare, or your crib sheet, you should definitely do the same thing where you write down common random variables and their means and their variances, okay? There is no table that corresponds to like common joint random variables, except for like the joint Gaussian, which we talked about last time, right? But it would be okay for me to say, okay, you know, suppose that x and y are exponential random variables, and one has lambda equals 2, and the other one has lambda equals 4, and then, you know, compute this thing for me. Then the idea would be that, okay, I could use my knowledge to say, okay, the mean of the expected value, or the mean of the exponential I know is 1 over lambda from my table, right? So again, my goal is not to make you do computations that you don't have to do. And I'm also looking for you to kind of know, okay, I should be able to do this more easily, right? Okay, so let me come back to this question mark of like, okay, I computed previously that this covariance was negative 1 over 144. Like, how do I really interpret that? What does that mean? So really, kind of what I want to do is balance that against how much x and y are kind of innately varying, right? So remember that the interpretation of the variance of a random variable was kind of like how much it spreads, right? How wide the possible set of values could be, right? And so, you know, the expected value of xy like this is the covariance, is hard to judge, or yeah, it's kind of hard to judge on its own. And so what we do is we normalize it with respect to kind of the variance of x and the variance of y to, you know, get a sense of kind of like the strength of the correlation. Okay? So, you know, 1 over 144 may not be that much if the variance of x and y by themselves are like 50, right? But if the variance of x and y by themselves are like 1 over 1,000th, then that tells me actually a lot more, right? It tells me that there's a big strong correlation. And so kind of what I want to do is I want to get a number that is always in the same range, right? So what I'm going to do is I'm going to define what's called the correlation coefficient. Oh, question? What's that word? Oh, I'm sorry, yes. I guess I just, so this is WRT. WRT stands for with respect to. That's some professor's shorthand for you, right? Sorry about that. Wort. Okay, so what I'm going to do is I'm going to define what's called the correlation coefficient, which is something that if you ever took a class in statistics or something, you may have heard this before, called rho, which is the covariance divided by the standard deviation in x and the standard deviation in y, right? And remember that those were defined as basically the square root of the variance. And the nice thing is that, you know, nice property is that rho is always in the range from -1 to 1. And so actually I can prove that. So let me just prove it for a second, just for those of you that are curious why that's true. So again, this is a little bit of a mathematician's trick, but let's look, for example, at the expected value of this quantity, which should look kind of familiar from your homework with the Gaussian, right? We did a bunch of stuff that kind of resembled this. So let's suppose that I take this quantity and I look at the expected value of it, right? Now, I think we should be able to agree that if I'm taking the expected value of something that is a square, right, this thing is always greater than or equal to 0, right? It can't be negative. So I know this is true, right? And if I write out what this means, this is like saying the first part is like the expected value of x minus mu x over sigma x squared. The second part is going to be plus or minus 2 times the expected value of x minus mu x over sigma x times y minus mu y over sigma y. And then the other part is going to be the expected value of y minus mu y over sigma x squared, right? Now, by definition, actually, this thing, if I didn't have this thing here, the expected value of x minus mu x squared is just what I defined as sigma x squared, right? So when I divide this through by sigma x squared, I actually get 1, right? So this is 1, and this is also 1. And this is actually, if I think about it, this is the definition of the correlation coefficient, right? So this is the covariance, and then when I divide it by these two things, I tell you that that thing is called rho, right? So basically what I have is 1 plus or minus 2 times this correlation coefficient plus 1 is greater than or equal to 0. So kind of what I get is that my correlation coefficient is plus or minus like this, right? And so what I end up with is that the absolute value of this thing is less than or equal to 1. And that's what I found out, right? So basically, no matter how widely x and y vary, when I normalize by this pair of standard deviations, I get something that's in a nice interpretable range. And that means that once I obtain this correlation coefficient, then I can look at the two random variables and say, okay, well, what does this number actually mean, right? And it's not a coincidence that the rho that I'm talking about today, there was also a rho in the definition of the Gaussian joint PDF, right? There was this whole big thing, and you guys did it, I guess, in homework 14, where you had to plug in rho for something, right? So that rho is the same as this rho. And so in some sense, the Gaussian PDF is nice because it gives you all these kind of things that you normally want to know about the Gaussian anyway. It gives you the means, standard deviations, and correlation coefficient all in the definition of the PDF. So you don't have to go and compute anything that's already like right there, okay? Questions or comments about this? So how do I interpret this? What does this mean, right? So, and that's the kind of interesting part, is how to interpret the correlation coefficient. Interpret this rho. Well, if the correlation coefficient, and sometimes I put a little xy underneath it just to kind of indicate what two random variables I'm talking about. If it's equal to 0, right, that's like saying that the covariance of the two random variables is equal to 0, right? Which means things are uncorrelated. And kind of what that means in terms of if I were to look at kind of a scatter plot of samples of x and y, so if I were to look at, you know, I do my experiments and I observe x and y, kind of what I would get would be a bunch of dots that kind of just are, you know, generally, you know, uniformly distributed in the plane. I guess that's kind of hard to see. Maybe I should make these dots, you know, red. That takes me more effort to draw, though. I'm not going to color in every one of these dots, right? But basically, I kind of get a cloud of dots that doesn't really seem to have any sort of predictability, right? Now, when my correlation coefficient is high, suppose I get a high positive number. So let's suppose I've got like rho of x is greater than 0. Then kind of what I would expect to see in my scatter plot of realizations of these random variables is something like, you know, this, where the realizations show that there is kind of a trend where if x is big, then y is also going to be big, right? So that's kind of like saying, you know, small x is likely to produce small y. Not certainly, but certainly in a probabilistic sense, right? And if the correlation coefficient is really close to 1, then what I see is that if I tell you x, I more or less know what y is, right? It's kind of like saying that there is fundamentally a linear relationship. So again, if I were to kind of draw the best fit line through these points, the correlation coefficient is kind of telling me how good is that line fit? How bunched up are these points around that linear fit? So rho equals 0 tells me that really I could draw a line through these points, but it wouldn't tell me anything, right? It's just like a cloud. Rho equals, say, 0.5 tells me that there is a relationship between these two variables and that one is slightly predictable from the other one. And rho equals 1 tells me that if you tell me x, I know for sure what y is going to be, right? And then what happens if rho is negative? If that happens, what it means is that there's a negative slope instead of a positive slope. So if rho xy is less than 0, then I could still have a correlation, but it would be kind of going the opposite way. So my best fit line would be saying that if I have a small x, I'm more likely to have a large y, and vice versa. And so you can see that this has lots and lots of implications for doing kind of real-world analysis of data and social science research and stuff like that, right? So, for example, if I measure my image quality in some kind of probabilistic sense, and then I measure how long it takes me to transmit that image, or how much bandwidth it takes me to transmit the image, then basically I kind of think that, low quality should require low bandwidth, and high quality should require high bandwidth, so those two random variables are going to be positively correlated, right? You can do studies that show that your income, at age 50 or whatever, is correlated with how much education you got, positive correlation. If you're a tall parent, you're likely to have a tall child, that kind of thing. And then conversely, there are things that are negatively correlated, right? So, if you look at the weight of your car and the miles per gallon, statistically, those things have a negative correlation, right? The heavier your car is, the lower the miles per gallon will be. Or the amount of TV you watch means that your grades are going to be lower, which I'm not really sure is true. I watch a lot of TV, and I got to where I am today. So, so it's not a foolproof method, but basically and so you're going to see if you read any sort of literature about looking at data analysis, people are always reporting this kind of R-squared value, which is related to the correlation between two variables in a more statistical sense, right? So here in this class, we're really concerned about the probabilistic interpretation. So sometimes people get a little bit uncertain about what's the difference between a probability course and a statistics course. So you'll notice that we haven't done anything in this class that involves tables of data that you use Python or MATLAB to crunch through and give me a number, right? We're doing more pie in the sky, what is the theoretical correlation between random variables, right? But all that statistical stuff kind of has this probabilistic formulation underlying it, right? So it's kind of the difference between using a table of real numbers and using the theory about if I knew what the joint PDF was, what would the correlation be, right? And of course, it's important that we have both sides of the equation because on the one hand, we want to know kind of what the theoretical limits of, say, image compression or something like that are, right? And on the other hand, we've got data in the real world that we can't possibly necessarily fit an accurate PDF to, right? We don't know what the real distribution of education, income is, so we have to look at data points and then measure the correlation empirically, right? Okay, so let me pause and ask questions, comments about that. Hopefully that answered your question about how to interpret the rho value, right? And so a good exam question, which I'm not sure whether it's on the back exams already, is kind of if I show you a picture like this and ask you to match with rho values, you might be able to kind of just look at pictures and tell me, is this big rho, small rho, negative rho, positive rho, right? So that's kind of, the kind of question I might ask. Yep.
As rho approaches 1, does it approach the line y equals x, or can it be y equals 2x?
Yeah, I guess I drew these all 45-degree angles, but what matters is kind of how closely things are clustered to the line, not the angle of the line itself, right? So I could also have, rho equals 1 be, something like this, right? That would still have rho equals 1. It would be a steeper slope. So it's more about how predictable one is from the other, not the actual slope.
Does rho always
is rho. So, oh, so yes. So the question is, does rho tell me about linear correlation? So, for example, suppose I had something like this, right, where clearly x and y are kind of related by a parabolic fit. The correlation coefficient is not going to tell me anything about that, right? The correlation coefficient will probably actually give me something that's close to 0 for this because the best straight line fit is going to be something like that, right? So yes, the correlation coefficient only reveals like linear relationships. Good question. Yeah.
So from that, is there a way to get a correlation coefficient that would be useful for?
Right, so okay, so now we could say what if I wanted to uncover patterns like this in my data, right? So I could correlate y with x squared and find a high rho value and then know that those things were correlated, right? And so that's typically what you might do in like kind of a quadratic regression. You'd say, okay, I'm going to correlate y with x squared, y with x cubed, and see if I can, you know, that's kind of like what, then you get into like things like polynomial fitting, right? That's how you fit points to data, is you try and draw the best curve through the points, right? So yes, you can definitely scale this up. Yeah. Good discussion. Other questions or comments? Okay, so last thing I want to talk about, because I know that you are all on the edge of your seats about it, is remember that we said in the beginning that independent random variables imply uncorrelated, right? But uncorrelated does not imply independent. That's an important thing to remember. And so I just want to do an example that shows that's true, and it's also a good exercise for kind of, again, just another bunch of examples of manipulating PDFs and marginals and stuff like that. And so let's suppose that I take this example, okay? So I'm going to have a diamond like this. This is going to be my PDF that ranges like this. And let's suppose that the joint PDF is equal to 1/2 inside this diamond, right? So it's kind of like a uniform PDF on this region. Again, why does that make sense? Well, this area, this line is square root of 2, this line is square root of 2, so the area of the square is 2. That means that I have to have the PDF equal to be 1/2 to make sure that everything integrates to 1, okay? So let's compute the covariance of x and y here. So first I'm going to compute the expected value of x and y, right? So again, this is a good exercise in like, again, many of you, I know I haven't done it in a long time, is, you know, you have to remember kind of how do you take apart the integral into the right pieces, right? So here, if I was going to do this integration, what I'm going to do is I'm going to choose kind of integration stripes that look like this, okay? And unfortunately, because of the fact that these lines kind of change orientation, I need to do this in 2 pieces, right? So the first piece is basically saying like x is going between -1 and 0, kind of the left side of these lines, that's dx. And in that region, y is ranging from, well, this line here is like, let's think about this. This line here I think is 1 minus x, and this line is minus, oh no, sorry. This line is 1 plus x, right? X plus 1 and minus x plus 1. Let's just make sure that makes sense, right? So when I'm at -1, I plug this in and I get 0 to 0. When I'm at 0, I'm going from -1 to 1. That makes sense. And then I plug in my PDF, which luckily is just 1/2. And then I have to multiply that by xy, which is the part that comes from evaluating the covariance. So that's the left-hand part. The right-hand part, x is ranging from 0 to 1. Y is ranging from, this line has a positive slope, so this must be like x minus 1. And this goes to 1 minus x, right? So if I'm at 1, I get 0 to 0. If I'm at 0, I get minus 1 to 1. Everything is good. Okay, so now I have to do this integral. So I'm going to get 1/4 x y squared between y equals x plus 1 and y equals minus x plus 1. This integral, oops, no, not this integral, minus 1 to 0 dx. This is just the first part, so I'm just doing part A and part B. So part A is this. So, blah, good times. So let's see, what am I going to get here? At least I can take the x out. So I'm going to get, did I do this right? Hold on a second. I'm doing this dy. Yeah, 1/4, yes. No, I feel like I already did something wrong here. Oh, you know what? This is okay, because actually life is easy. Because if I plug in y equals plus something and y equals minus something, that actually I'm going to get like 1/4 x. I'm going to like get x plus 1 squared minus x plus 1 squared. You get 0, right? So this integral is going to be 0. That's nice. And this integral, I think, is also going to be 0 by the same token, right? So if I were to do this integral, I think I get 1/2 1/4 x y squared. Again, I'm going to plug in these two things. So actually, I feel pretty good this is going to be 0 overall, right? You can convince yourself of this if you really want to do the integration, but I realize now that this is a good way to set it up. So certainly the expected value of xy is 0. Let's think about what the expected value of x by itself is. Well, what I'm going to do is I'm going to squish down this thing to compute the marginal, right? So what is the expected value of x going to look like? It should actually be kind of easy to see that all I'm doing is I'm kind of like mushing down the probability. It's going to be 0 at both ends, and it's going to be high in the middle. And actually, I can see it's going to kind of look like a triangle, just like this does. So let me just show why that's true. So what is the marginal of x? It's going to be the integral from minus infinity to infinity, the joint where I don't care about y. And so what are we going to have? I'm going to say I'm going to be going between, if x is less than 0, I'm going to go, actually I'm doing the same integral I did over here, right? I'm going between minus x plus 1 and plus x plus 1, the integral of 1/2 dy, which is going to be equal to 1/2 times y evaluated at these places. And since I plug this in, I get the same thing. I'm basically going to get 1/2 times 2 times x plus 1. So I'm going to get x plus 1 if I'm in the range x less than 0. And it turns out that by a similar, if x is greater than 0, what I'm going to get is the integral like this from x minus 1 to 1 minus x of 1/2 dy. That's going to look like 1/2 times 2 times 1 minus x, which is 1 minus x if x is greater than 0. So kind of the PDF, what I get is going to look like 1 minus the absolute value of x. That's kind of like my overall PDF. And it looks like, it just looks like this, right? So this is the marginal in x. Again, this is good, right? Because I got a triangle that has a half area here. This triangle has half an area, so this adds up to 1. Everything is good. And I can see actually everything is symmetric. I didn't even need to do this to be able to prove to myself that the expected value of x is equal to 0, right? Because it's symmetric around the middle. I could have concluded that from this picture, but I decided to do the math. So what did I learn? I learned that the expected value of xy was equal to 0, and the expected value of all this other stuff was equal to 0. And so the covariance of these things is going to be equal to 0 because it's 0 minus 0, okay? So these two random variables are uncorrelated, right? That's what the definition is because I got this result. However, these random variables are definitely not independent, right? So, but these random variables are not independent. Why is that? Let's think back again about the joint PDF. Looks like this. So, for example, remember what we need to have for the PDF to be independent would be that the PDF decouples into an X part and a Y part. And I can see here that, for example, you know, the PDF of X at 3/4 is basically like the marginal over here. It has some value, right? It's not equal to 0. And in fact, it's equal to 1/4, right? And in a similar way, by symmetry, the PDF of Y, it's possible to get 3/4 there too. But the joint PDF of getting both X and Y equal to 3/4, that's like saying I'm out here, right? That is equal to 0. So this is definitely not equal to the product of the PDF in X and the product of the PDF in Y, right? So the bigger X is, you know, clearly I can't get big values of Y. So that's kind of important to just realize that even though I could have kind of the numerical coincidence that the correlation coefficient and the covariance are 0, I could still have some sort of statistical relationship between the random variables, right? And so that's kind of like, what's the right word? I mean, I guess it's not quite the same as the old adage about correlation not implying causation. It's kind of like saying that, you know, just because things are uncorrelated doesn't mean they're not related, okay? And that's kind of something to remember when it comes to real life too. So the only case where it is true, actually, or one special case where it is true, one special case where if I tell you that things are uncorrelated, and it turns out that uncorrelated and independent are the same things, is the joint Gaussian. And we actually showed that in the last lecture, because I remember that we basically said that if the rho in the Gaussian PDF was equal to 0, we actually proved that the joint Gaussian kind of split apart into two Gaussians multiplied together and vice versa. But this is only in the case, or this is certainly only true in the case of Gaussians. I mean, it's not generically true, as I showed in the left half there. Okay, so questions or comments? All right, so this is the end of the kind of material for exam 2. So basically, what did we cover since exam 1? We talked about continuous random variables, you know, kind of all the stuff in terms of PDFs, CDFs, expected values, and then we amped it up to 2 random variables and talked about the same things, and then we added a little bit of extra twist today about how those 2 random variables can be related, okay? And then just to kind of give you a preview, what's going to happen after exam 2 is kind of more, a little bit deeper stuff about, okay, what can we do, for example, if I want to take one random variable and predict the other random variables. More like real world stuff that kind of is like a little bit of an introduction to pattern recognition and machine learning types of things. Okay, so that's it. See you next time.